So the lab that we're doing today is going to be investigating the stuff we've been learning about friction. All right, so what we're going to have is a surface which is going to be the back side of the ramps that we used from the tracks that we used from the other day, the wooden ones. Okay, but don't use the side with the grooves, use the flat side. Okay, and what we're going to do is we're going to be investigating the relationship between normal force and the force of friction, okay, in this formula here. Okay, now, according to that formula, as normal force goes up, what should happen to friction? It should go up. Okay, now, the way we used to do this was we used to put these little wooden blocks on the floor, and we would just pull them, okay, with like a spring scale and try and get a good reading on when they would start to move. Okay, because that instant would be when you finally overcame the force of static friction. Right? And so you could, just by looking at the spring scale, you'd know what the force of static friction was the instant you overcame it. Okay? The problem with that is it's really hard to get a good reading that way. Okay? So Mr. Dickey and myself thought about it. We said, what's an easier way to be able to observe the maximum force of friction when something starts to move? And we decided it's with the use of an inclined plane. Okay? So what we want to do is we're going to have our friction sleds, that's these wooden blocks, and we're going to have them on our ramp. Okay? So we're going to set them on there, and we're simply going to put our phone next to it with the clinometer on there so that you can read the angle. Okay, so that works. So if you have an iPhone, it's in the Measure app. Okay, so if you click on the Measure app, it will give you Measure, which I have still not figured out how that actually works, and I've never gotten it to work. Or the other option is Level. Okay, so if I...
I'm trying to think, like does compass work as well? Because technically it does work at an angle.
Well, but compass is taking a north-south reading.
No, I know, but if you swipe to the right on it,
okay,
it shows you like the
That's
angle.
probably the same thing. I just used the measure part.
Okay.
Whatever way will get you the clinometer makes no difference. That's all we need.
Okay.
Okay? So what we're going to do is one person's going to put their phone on the ramp. Okay? And this one is showing that this is nice and flat and horizontal. Okay? And then we're simply going to increase the angle. And as soon as the sled starts to move, that's the angle we record. Everybody with me? Okay? Just as it starts to move. And you got to go slow. Okay? If you just go like this, you're going to miss it. Okay? You got to go really, really slow, be really methodical about it as you lift that ramp. Okay? Having somebody watch that angle. Do it as smooth as you can, nice and slow. All right, there it is. Okay? Same? Pretty close. Okay. All right, so that's what you want to do, okay, with that. So what we're going to be kind of measuring / recording here is we have to know the mass that's on the cart. Okay? Just the wooden block is 0.254 kilograms. Okay? The smallest mass that we're going to start with is this block fully loaded. Okay? So you'll have to add all the masses that are in here, and they're written in grams. Okay? It's not funny. It's called time, and it knows where you live. It's coming for you too. Okay? All right. So it's okay. They're written on there they're engraved on the masses. So you'll just have to add it all up. So 254 plus whatever's on here. Okay? So that'll be your first trial. When you do this, you have to make big changes in mass between trials, and we would like to get 5 or 6 data sets. Okay, to fill in. I think on yours, how many rows do you guys have on your chart there?
6.
6, right? Yeah. So try and get 6 trials. So you're going to use that mass block plus one of these mass sets from the other day. All right. So on this one here, you're going to have I can't even remember what that's going to be the mass of. Okay. And then on the next one, like put a fair amount more mass on there, like a few of these ones, and and then throw a half kilogram on there, throw a kilogram on there. Okay, if you need 2 mass sets, that's fine. Okay, I think on my trial data, I got up to like 2 point something or even 3.5. Hang on, let's have a quick look here. Yeah, my biggest mass was 2.75 kilograms. Okay, in total, including the sled. Okay, so what I had for mine, and you don't have to replicate this, but what I used was 0.35, 0.75, 1.25, 2, 2.35, and 2.75. Those are the masses I used. So you can see, I make fairly large changes between each trial for my mass. Okay, like several hundred grams each time. Yeah, like this was 400 grams, this was 500 grams, this was 750 grams difference. Okay, this one was only 350, but I was starting to run out of masses, I think, and then 400 grams. So I'm making big changes in between each trial so that I get big differences. Okay, so as I increase the mass of this cart, okay, what's really going on here, okay, is, I don't have a diagram of it, I thought I did. Okay, so I'll just draw it. So I'll have my inclined plane. Theta is going to change because that's what we're observing, and it's hopefully responding to what we do. Okay, because there's actually more than one responding variable in this lab. Okay, in this lab, just from a design point, okay, we said we were wanting to compare these 2 forces, normal force and the force of friction. Okay, by adding more mass to this, what am I changing? Well, yeah, I'm going to change that too, but what am I changing on purpose by changing the mass of this? That's going to change as a result. What am I changing on purpose by adding mass to this? One of those 2. Normal force, right? The more weight there is, the more normal force there is. Agreed? Everyone all right with that? Okay? And yes, lots of other things are going to change. Okay? F parallel is going to change. Okay? The force of friction is going to change, right? Things like that. So, setting this up, and this will help you get some of the other variables. Okay? I'm going to change the mass of this block. That's going to change the force of gravity, but that's not really important for our lab. What's really important for our lab is the relationship between that force and that force. Okay? We're dealing with static friction, which occurs when the object is stationary. Okay? So we're finding that maximum angle, which is also responding, okay? But we're finding that maximum angle before this starts to slide. Okay? So before this starts to slide, what's the net force on the plane? 0. So what does that mean about that force and that force? Right. That you need to know. Okay? Because the only way we get the force of friction in this lab is by the fact that it's equal to the force parallel, which we can calculate ourselves. Okay? We don't know the coefficient of friction for this lab, so we can't use the formula to calculate the force of friction. We're actually going to use the fact that we're using static friction and that the force down and the force up are equal. And we can calculate the force down because we're going to measure this angle, okay, whatever it happens to be, and as a result, we'll be able to calculate this number, and that number. Okay, knowing that F parallel and the force of friction are going to be equal at the instant it starts to slide. good with that? Okay. Now, when I do this lab, other things that could affect the force of friction, right? We know that normal force can affect the force of friction. What's the other part of that formula?
Coefficient of friction.
The coefficient of friction. Now, I should probably be mindful or controlling of anything that could affect that coefficient of friction. Because in fact, in this lab, we're going to try and figure out and calculate what it is. Okay. Should it be the same every time I do this? I hope so, because I'm always using the same sled and the same, what? The same ramp. In order to make sure that this interface is always exactly the same, what do you suppose I should do between each trial? Like, my first trial, I'm going to do this. Okay, it started to move.
Read level, like make sure it's level.
Well, the level's not going to be important because I'm measuring the angle. Right? That's going to be different each time. I mean, you're right. I want to start from here each time, for sure. Okay? But what else should I make sure of before I put this back on there? If I put two blocks together and they slide, does that have a sanding effect? Could that change the interface? Anything that can affect the coefficient of friction or the force of friction needs to be controlled in this lab. And that's one of the things right there. I got to make sure that interface is the same, or as best I can do that each and every time. Okay. All right, so for our hypothesis, okay, we want to have it talking about the relationship between normal force and friction. Okay, so the if part just needs to talk about that. Okay, what kind of relationship is there as normal force goes up? Okay, what happens to force of friction? The and part, as always, is going to describe the experiment. And the then part needs to tell me what's going to happen in the experiment in terms of like angles and things like that. But also, how will you calculate mu using a graph of normal force versus the force of friction? Okay, so one of the things you're going to do in this lab is build a graph of normal force versus the force of friction, making sure your manipulated variable is on the x-axis, okay, and your responding variable is on the y-axis, okay, and then making your graph, and using your graph, how can you get the coefficient of friction? Using your graph. I cannot stress that enough. I don't want to see 6 separate calculations using the formula. I want to see one calculation using the graph. Okay? Okay, and all right, so we'll have that. So you'll have the ramp angle, okay, and then obviously the ramp angle will be used to calculate F parallel, which we said is going to equal our force of static friction because the net force is 0 in this situation, okay? And we'll also need to calculate normal force because that's got to go on our graph, and we need the angle to do that, okay? Because we have to remember that normal force is the cos of theta times Fg, and that F parallel is the sine of theta times Fg. That's just inclined plane stuff, okay? Like finding that internal triangle things before, that's nothing new for us, okay? All right, so your analysis is pretty simple, okay? You're going to put your value for normal force in here, which we already said, okay, that's going to be cos of theta times Fg. Your static frictional force, which is going to be F parallel, sine of theta times Fg. You're just filling in this chart, building your graph, and okay, show me your calculations of the coefficient of static friction. Okay, and then I would like an explanation here as to why your calculations actually calculate mu. All right, so we're looking for a couple sentences, okay, explaining why what you calculated represents mu. Okay, so there's no like analysis questions. Okay, you're showing me one calculation and explaining why it's valid for calculating mu. Very good with that? Okay, then for your conclusion, copy and paste your hypothesis, same as always. Okay, and then tell me whether your data and analysis support it or not. Sources of error, ways to fix them. Okay, two sources of error, and ways to fix them. Right, you don't have to do the class discussion. We've actually already talked about most of those situations already. Okay, all right. Questions from you guys? All right, I'm going to put those masses that I had back up on the board. Okay, and you guys you don't have to do those exact masses. You may not even be able to replicate them completely, but know that you need to make big jumps of around those numbers, okay, when you're performing the lab, okay? But the really big thing is be careful, be thorough, okay? Really lift this thing slowly as you go up. I would suggest that probably, like, on this desk is probably fine, but there's one thing you have to know about the desk. Is the desk level front to back? It's not. Okay, so if you want to do this to save your back, like that's what I do because I'm old, okay, where you guys are young, maybe it's better on the floor because the floor is more level than the desk. I won't say it's perfectly level, okay, but it's more level than the desk. Okay? All right, if you have questions while we're doing the lab, just ask. Okay? Now, one last thing. You may have an initial thought as to what your data is going to look like. And I'm going to caution you that it may not go that way. And if it doesn't, it's okay. I don't want to bias you too much, but this happened to me. This last time we did this was the first time we did this, and I did it and I got frustrated. And I was really upset with myself because it didn't seem to be giving me the data I expected. And then I had a facepalm moment after that, when I realized that it was doing exactly what I wanted, and I just didn't realize that that's what it was doing. Okay, so if you're thinking about, one thing should happen as they increase the mass, it may not, and that's okay. Okay, just take your data, and then when you do the graph, you'll see that it worked out the way it was supposed to. Okay. All right, one group can use this apparatus if they want. Okay, other groups come up and get the stuff we need. So one block.
So do we keep these in here and add these?
Yes.
Okay. And like,
And what do they do with the fun tack? Oh, guys, there's fun tack up on the board as well. You'll probably want that because if you don't, those masses will move around, and you don't want that because they'll help it get moving if they start to move. Okay, so take a little fun tack to keep those masses from moving.
do you want to do it on the floor or on the desk? And these are in grams, right?
That's for floor. He said floor is gonna be